Okay, Raju, take it away.
Okay. Good afternoon, everyone. Welcome to the Geospatial Forum. And it is my great honor to introduce today's Geospatial Forum's distinguished speaker, Professor Pankaj Agarwal. We are GI scientists, and especially in particular, if you are following GIS literature, in particular ACM SIG Spatial GIS, Dr. Agarwal doesn't need any introduction. But still, let me, people who are new, who are from other disciplines, let me tell few things and his connection to GIS. Um, he is well known, like world leader in computational geometry, which is a critical component that is driving our GIS systems. And Agarwal has published 4 books and more than 350 articles, research articles in leading journals, and which collectively received more than 26,000 citations. And that is more than 2 or 3 lifetimes of achievement. Getting those many citations is not easy, especially in particular, you are working on very niche field like computational geometry as compared to machine learning or AI or something fancy fields where you have tons of publications where you can get a lot of citations. Dr. Agarwal has given numerous invited talks, including he was a keynote speaker a few years back at ACM SIG Spatial GIS. He is a fellow of ACM, which is the world's largest educational and scientific computing society. And he is a Sloan Fellow, and he is one of the US National Young Investigators. Dr. Agarwal received his PhD from, again, very well-known, prestigious Courant Institute of Mathematical Sciences at NYU. And then he joined Duke in '89, where he is currently a named professor, Nabisco Professor of Computer Science, and also Professor of Mathematics. And he served the computer science department twice, not one. One is again lifetime achievement. He served it twice, and hopefully one more time, I guess. And he's the and he published so many papers, like I said. And as a grad student in Minnesota, I read some of his papers when I was doing spatial database research there. And I'm sure a lot of you are also familiar with that. I will let us invite Dr. Pankaj for giving this lecture in our forum. With that, I will turn the dais to Dr. Pankaj.
Thank you, Raju, for a very kind introduction. First, it's good to be back, at least virtually. As I was telling Raju and John that I have not been to NCSU for a while now. I have given multiple talks at NCSU, but many years ago, and it's good to be back. And also, I should say that I don't know if Helena is an audience, because what I'm going to talk about, a lot of it started in collaboration with Helena. We go a long way. We collaborated for many years, I think starting about 20 years ago. I had number of multiple joint grants, and she was good in telling me or teaching me some of the geospatial stuff. So that brings me to, as Raju said, I'm not a hydrologist. I'm not an expert in geospatial. I'm a computer scientist, work in algorithms, especially geometric algorithms. And geospatial is a very good source of data and motivation to work in geometric algorithms. So in this talk, you will hear an algorithmic perspective on geospatial data and flood risk. So I'm not a modeler, I'm not an expert in modeling. So, and I rely on people like you and Helena to inform me. I use simple models but focus more on algorithms. So with that disclaimer, let me begin. So let me see. Just a minute, I'm having some technical problem.
Yeah, that's fine.
Because I'm not able to Can you see my screen?
Yes, but only the title slide. It is not
Yeah.
advancing.
Okay. So,
Oh,
so
yeah.
for some reason, my let's see.
Yeah. Yeah.
So, so for a number of years, uh, high and high resolution data, geospatial data is being collected. So for example, one of the early ones is in 2000, there was a space shuttle mission, that 11-day mission that collected at that time what's considered very high resolution data at 90 meter at 3 arc-second resolution. And it took them NASA a long time to clean up the data, prepare the data, and release the data. Then there was another mission by NASA, joint mission by NASA and Japan Ministry of Economy. They increased the resolution to 1 arc-second, so about 30-meter resolution at equator. Again, it took a long time and covered most of the Earth. But later then, because of a lot of LiDAR, now we are sort of in the LiDAR era, and the LiDAR data has been collected in higher and higher resolution. So some of the early data sets, this is some of the data sets I worked with the Helena, was at that time were News River Basin and 10 feet or 5 feet resolution. Then I had collaborators in Aarhus University working with them. So first with the whole Denmark data at 30-meter resolution, and then we also got at 1-meter resolution. That so data is about some billions of points. So just to give another example, so for the Scandinavia, so we have the data set for Denmark at 40 centimeter, for Sweden 2 meter, for Norway 1 meter, and these data sets together have about 700 billion points. So the first question that comes is, which I don't have to convince you, is it really important to have high resolution data? Does it matter? And the answer is yes. Let me just give you one example. So it's not just about that you get more accuracy. Oh, I should say that before that there is a USGS has this program, 3D elevation program, that is collecting most of the data on US at 1 meter resolution. And this is an old numbers. So I think about 2 years ago, 1.5 years ago, they had already had 12 terabyte of data. And I think now it's much bigger, the data set. So why do we care about high resolution data? So this is an example of a small island near Sweden, and it has a dike around it. So when you look at the 2-meter resolution, the dikes are captured, and when you do the flood simulation, the island is not flooded with a little bit of rise in sea level. But when you look at the space shuttle, the original mission data, which was at 90-meter resolution, and if you look at the same data set, if you run them, the dikes are not captured. So even if you just do a little bit of sea level rise, and the whole island is flooded. So it's not just about you get slightly more, but the topology changes because you can, by having high resolution, you can capture very fine topology, and that makes a big difference. So number of work sort of, I have collaborated with people in US Army, and for them, that sort of, it makes a big difference whether it's a 30 centimeter versus 3-meter resolution. So we need high resolution data for doing the accurate analytics, and we are getting high resolution data becoming increasingly easily available. So what we need is now, in order to take the full advantage of these data sets, one needs techniques, algorithms to process them and model these data sets, analyze them. So this is what I have been doing. What I have been doing in collaboration with a number of people is developing scalable algorithms for modeling and analyzing terrain data. That's one of the sort of my projects have been, and worked on different components. One of them is construction of DEMs, and this is one of the places, the things I did with Helena, looking at water flows, contour lines, watershed hierarchies, and so on. Today, I'll focus on only one component. I'll focus on flood risk management, developing algorithms for flood risk analysis. Please feel free to interrupt me and ask me questions. And I'm not good at monitoring raise hand, but John and Raju have promised that they are paying attention and they will interrupt me. Okay. So flood risk, as we know, they are everywhere. So the left figure is from New Bern. for a couple of years ago. And these are pictures from different continents. So it's the flood. All of us are, doesn't matter which part of the earth we are facing the flood risk, and it's increasing more and more with climate change. There are broadly 3 different types of floods. Fluvial flood, this is on the left, is a News River. I think this is near Goldsboro. The second is what we call pluvial flood, heavy rain, flash flood. This is a picture from my neighborhood from Chapel Hill. And the left is a what we call a sea level rise when there is a storm, the coastal flood. I'll mostly focus on a pluvial flood. So what I'll do is I'll first define the problem mathematically, tell you what kind of questions I'm interested in, and then share with you some very high level, some of the techniques that we have developed. Okay, so first, what is the model we are using for representing a terrain? So I'm using just good old tin representation. So we have a triangulation in the plane. For every vertex, there is a height associated with it, and we are assuming linear interpolation within each triangle. And the data is pretty high, so whether you can sort of do more sophisticated, it doesn't make that much difference. And throughout this talk, I will use this letter N to represent the number of vertices on the triangulation. And when I talk about the algorithm, we'll measure its performance in the number of vertices. Okay, so this is the model for the terrain. For water flow, so we assume that we are given a region on which a rain is falling, and there's a distribution given for the rain. It may be uniform, it may be not uniform, and we can also tell how long the rain is falling or what is the total volume of that rain that has fallen. And from every vertex, we assume the water flows along the downslope edges. So we are assuming that the water is flowing along the edges. We are not assuming the water flows the interior of triangles. All the water is flowing through the edges. And this assumption is reasonable because the data is very high resolution. So we can focus on just assuming the water is flowing along the edges, and that keeps the things simple. And the water flows along the downward edges, and when it reaches a sink, it starts accumulating there. And so regions start getting flooded. Okay, so how does, there are different models for the flow. The most popular one is what is called single flow direction model, that assumes that for every, on the left side, so here, the water from vertex, water flows only along one of the edges, on maybe steepest edge, or whatever the model one can use, but as the assumption is water flows only along one edge. And the multi-flow direction is the water is flowing along all the edges, and what proportion that we can use slope, or one can use any kind of model that one wants. So it's not so important. Multi-flow direction model is more realistic, but is much more computationally much more challenging. So at least in GIS community, the most of the work has focused on single flow direction model. Okay. All right. So once we talk about the flow of the water, then let's say, then how do the areas get flooded? So let's say the rain is falling on the point P, and we have depressions on the terrain, and you are monitoring point Q. So as the water starts falling here, let's assume a very simple example, trivial toy example, that the rain is falling on a single point P. Then this depression start getting flooded, and the depression is full. Then the water starts spilling over to the next depression. And when this depression also gets full, then the whole thing is full, then the bigger depression that has started getting full. And once that is full, then the water starts spilling over from there. to the next depression, and so on. And eventually the water will reach Q. So this is a very simple flooding model we're talking about. And when the water starts spilling from one depression to another depression, we call that as a spill event. And the bottom figure is showing the depressions and how they're sort of getting filled, is showing the contours. Okay, so now that I have described the terrain, the model for the terrain, for the water flow, and for the flooding, now I can talk about the specific questions that I'm interested in. So the simplest question I'm interested in is, we are given a terrain, we are given a rain distribution, and the volume, total volume of the rain. Tell me which points on the terrain will get flooded. And we can also ask how much water will be at a given point, or all the points. Now, so this is a question that many government agencies are interested in because they're interested in more global picture. But as a user, I might maybe more interested in what happens to my home. If this rain is falling, whether my home will get flooded. So instead of the entire terrain, we might be interested in on a single point. If there's a given a rain distribution, whether a single point Q, let's say, whether this point Q will get flooded. Insurance agencies are also interested in this question because when they're looking for the flood insurance, that's why they're interested about a particular house. What is the probability that if there's of that house will getting flooded? So here there's no temporal. It's a more sort of static query that I give you the rain distribution, I give you the total volume of rain, tell me whether which parts will get flooded or which point will get flooded for a specific point. We also may consider a slightly more complex query that suppose I give you rain distribution and the rain distribution is varying over time. For simplicity, I'm assuming the rain distribution is kind of histogram as a function of time, piecewise constant function. And then what I want to know is what is the flow of rate of water on each vertex or each edge on the terrain. So want to compute the flow rate at different vertices or different edges of the terrain. So those are the three high-level questions I'll focus on. If I have time, I'll talk a little bit about some other questions as well.
Dr. Agarwal?
Yes.
There is a question by John.
Hi, John. Yes.
He's asking about how do you account for permeable surfaces?
That's sort of a good question. Right now, in this talk, I'm assuming that it's a kind of a, what is sort of a glass, sort of the water doesn't go in the surface, it's filling. But we can extend it. We can talk about that, how much when the water flows, how much flows or how much it gets absorbed. But in this talk, I will not talk about the absorption.
Okay, but your model is general enough.
Yeah, model is general enough. Yeah. One can do it.
Okay.
But I'm happy to talk offline and explain to it how one can do it. But for the simplicity, I will just there are a lot of issues I will ignore in this talk.
Okay.
Okay. So before I talk about the techniques, I need to introduce a few concepts. So most of them, all of them are from topology. The first one is what we call critical vertices or critical points on a terrain. So a typical vertex is what's called a regular vertex. Some vertices they have some upslope neighbors and some downslope neighbors, and then they form a connected portion along the neighborhood of the upslope, and there is a connected neighborhood of the downslope. Then there is a sink minimum, where all its neighbors are upslope neighbors. Then we have peaks, there all the neighbors are downslope neighbors. And then we have saddles, that as you go around, as you find some upslope neighbors, then you find downslope neighbors, then again upslope neighbors, and then again downslope neighbors. So this is the saddle. Or even have saddle here, which are sort of, this saddle is connecting two peaks, like at this point, the two peaks split. Then the other saddle, which is called negative saddles, where two depressions meet, like this is sort of all this saddle. Since we are talking about the water flow and the water is flowing downward, we'll be mostly interested in sinks, minimum, and and the negative saddles. We will not be so interested in the peaks and the positive saddles. Okay. Once we have defined critical points, next notion I need is the notion of merge tree. Oh, I should go back and say one more thing. So the one concept term I will use throughout the talk is a depression. So mathematically speaking, depression is a connected component of a sub-level set. So that is that you fix a height to take a level set. And so suppose you cut the terrain at fixed height and look at the below. So below the plane where you cut it, there will be different connected components. Each connected component is called a depression, because that's where the water is being accumulated in depressions. So the merge tree captures the topology, how the topology of the depressions change with height. So for example, here is the toy example figure. So when you are at very high level, so if you look at the below this height, then there's only one connected component, and then there's only one depression. So this is captured by this one point. When you cross through the first saddle, here in the 2D it's maximum, but in the 3D, once you cross the saddle, this depression is now splitting into two depressions. And so that's why one has a tree left. These points correspond to two depressions. So each point in this tree corresponds to a depression for at fixed height. If you go further pass through this saddle, then this depression is now splitting into two depressions, and so on. So this way you get a tree structure, and this tree is called merge tree. And the merge tree can be computed quickly. There are fast algorithms for computing this merge tree. And the merge tree can also be used to compute volumes of different depressions quickly, which will be useful. Okay. Once I define merge tree, I need what I call tributaries. So suppose any point on the terrain, if you have pointed terrain, it can be mapped to one of the points on the merge tree. Basically, so you think about this point and you look at the depression. If you look at the level set passing through this point, then this point lies on the boundary of a depression, and the corresponding point, the depression on the merge tree, I map a point on the terrain to that point. So if I give a point on the terrain, I can map it to a point on the merge tree. So suppose you have a point on a merge tree, on a terrain that I map to a merge tree, then I can talk about the tributaries of this point. That is, if you go from the root to this point, at each saddle, negative saddle that you have two depressions. Q lies on one side, and there's other depression. So the depression that do not contain Q at this saddle, like this depression or this depression and this depression, they are called tributaries of Q. So in this area, Q has three tributaries. Okay. Now let me sort of summarize some of the results. So going back to the terrain flood query, that if I give you rain distribution, I want to find out which points of the terrain get flooded. We have an algorithm that can compute this, answer this query in n log n time. So n is the number of vertices, and n log n is like, it's kind of sorting, that if you want to sort some numbers, that's what time it takes. In most applications that we're looking at, n is hundreds of millions or billion points. So if you want to have a scalable algorithm, you want to spend time, which is what is called roughly linear in the number of vertices on the size of the input size, because if you have quadratic, that just becomes too expensive for this large data set, and it's not practical. Second thing, for the point flood, if you are interested on a single point, whether if I give you a terrain, you can pre-process the terrain, do some processing of the terrain. Then for a given rain distribution, and for a given point, I ask the question, this point will get flooded if so much rain falls in this region. then you can answer this query after some processing faster. You don't have to run from the scratch on the entire terrain every time. And the running time depends on whether I'm looking at the single flow directional model, that the point flows only in one direction from a point, or multi-flow direction. In a single flow direction, one can do it very fast in log n time plus the complexity of the rain distribution. In the case of multi-flow, it depends on the number of tributaries. Do it. For the flow query, if I want to figure out the flow rate along all the edges and vertices, that also we can do after computing a merge tree, because if a rain is falling on one region, then the whole terrain doesn't get wet. It's only some portion the rain flows, water flows only some part. And so we can compute it in the what is the total output size, roughly in the output size plus times some log n factor. Now, one thing I should say is that all the running times I mentioned, and this is the only slide on which I'm mentioning the running time. This is I think the most CSC slide. These are the running times for the what we call the CPU running time. So assuming the data is sitting in your main memory, how much time does CPU take? To sort of get sort of a ballpark, if you're about 100, it takes about, all these algorithms, they take about, can process 1 million points per 2 seconds. So if you have roughly 100 million points, it will take about anywhere between 90 to 200, depending on the instance doing it. Now, when the data becomes large, like as the examples that I was giving, when you had billions of points, and the data is not sitting in the main memory, it is either stored in disk or it is stored on a remotely, then the communication becomes a bottleneck. So suppose the data is sitting in a disk, then the data has to be brought from disk to the main memory. And that's much slower. And that becomes a bottleneck in the computation. CPU is no computation, running time is no longer the bottleneck. So, and you don't want to, so suppose if you don't want to have sort of call n calls to the disk. What you do is you take one block of the data from the disk and store in the memory and process it, and then get another block of the data from the main memory. So this is called the IO model. And there are now more sort of general models. So one question becomes that are these algorithms scalable? Can they also be made communication efficient so that the data transfer, data communication doesn't become too much bottleneck? And the answer is yes. I'm not writing all the bounds and describing the model formally, but these algorithms can also be made IO efficient. And so that's communication efficient. Okay, so what I'll do is I will focus on the terrain flood and then flow query. And I'll say briefly about point flood query. Okay, just to remind you, the question at hand is, I give you a terrain, give you a rain distribution and total amount of rain that is falling. And you want to answer whether which points of the terrain or which vertices of the terrain get flooded. So to answer this question, what we do, the first thing, we build a merge tree, so that we have how the depressions change as you go or change the height. All right. So here is the main idea, and I will skip the details. I'll just tell the main idea. So what we do is we sweep the terrain from the top down. Now, here I'm sort of saying that I sweep through the entire terrain, but one can be more careful and one can sweep through only that portion of the terrain where that you know that it will get flooded, or we expect the flooding. There's no reason for one to sweep through the entire terrain. But for now, let's assume that I'm sweeping through the entire terrain. And what we monitor is how much rain is falling. So when you're sweeping, then you have some depressions. You keep track of all the depressions. And for each depression, you sort of check what is the volume of the depression and how much rain is arriving at that, water is arriving in that depression. So let's say in the beginning, we have only one depression. And let's say that the total rain that is reaching this 550 cubic meters, and the volume is 100 cubic meters. So all the water can stay inside this depression. So we go further down, sweep down. Then our depression becomes smaller. Let's say it's 90 cubic meter. So it is still all the water is staying here. One thing I should say here is when you talk about how much water, some water is falling directly from this in this depression, or the water might also be coming from some other depression because of spilling from some other depression. So we keep track of both. Okay, eventually, let's say you reach the first saddle point. At that saddle point, the depression gets split into two depressions. And now we have to do some processing and estimate the volume of each of these two depressions and how much rain is falling in each depression. And so we do that, and then we go and recurse both left and right in both a depression. So eventually what will happen is that we reach the depression that when it's sweeping down, that volume of the rain falling in that depression, reaching that depression, is the same as the volume of the depression. Then at that point, we can say this part of the depression is going to get flooded because of this rain, and we can stop. We go to the other side, we reach again a saddle point, and that depression is getting split into another two depressions. But if what you notice is that here the rain is falling, water that is reaching this depression is 20 cubic meter, but its volume is only 15 cubic meter. So some of the water will start spilling from this depression to this depression. So we need to keep that into account. Then this water, this left depression is flooded. So when we continue the right, and again we reach a saddle, again some water spills, and then eventually we will terminate. So that's what will happen. And then we will stop when there are no more depressions to sort of pursue. This is, I'm not going to describe. What the important thing is that how do I keep track of all the information, and how do I split the information and when I reach a saddle. Skipping all the details, what I show is that using some data structures and some techniques, you can do it quickly, spending by logarithmic time at each vertex. So the total time that we spend is roughly n log n time. So let me show the results on two data sets. One is urban area from Philadelphia, which is about 25 million points. On the right side, we have data set from Norway, which is, I think left side is about 3 meter resolution or 2 meter, I don't remember. And the right side is 100 meter. I think this is 10 meter resolution. So let me start sort of showing with some very simple thing. That suppose the rain is falling at only one point. And if I look at the single flow direction, the water is falling only one point, then as you can suspect that here, since the water is going to flow only along one path, so it goes and it goes to north and it gets accumulated some here and some here. But if you allow multi-flow direction on a point, then water flows in multiple directions, and some water goes for the southwest and some parts goes to now north as well. Now, this was just very sort of to show you the extreme, that the difference between single flow and multi-flow models. If the rain now is, instead of single point, it is falling on a region, then what you notice is that the way the water reaches, that's roughly, and if you look at this picture and this picture, it's roughly the same. It's not that different. And that's a reason that people sort of use single flow direction, because that's sort of good approximation. It's very quick to compute and it does some good approximation. But what you'll see the difference is, even though the accumulation of water is roughly the same, but how the water flows on the surface, that's very different under the two models. And SFD, it's just sort of straight line, narrow bands, and there it is sort of much more, it is spread across. And then there are also some differences at how much water gets accumulated in different areas. Okay. So this is a somewhat zoomed in picture on the bigger data set, on the same Norway data set. And you can see how the flow of water under the two models. So one of the, I'll say, is the main contribution of this work was that making the algorithms fast under the multi-flow direction model as well. And this is for the Philadelphia data set. Again, as you sort of suspect that basically at least under MFD, the water is sort of going along the main, getting sort of flowing along the main roads that you suspect. Okay, let me say a few words about the point flood. Now, if you remember that when I was sweeping top down, then whenever we reach a saddle, we were going on both depressions. And now, when you are interested only in one point, then when you reach a saddle, there's no reason for us to recursively compute the flooding areas in both regions. We just focus on that side that contains the point Q. So if you're in the merge tree, we sort of go along the path, and each depression we just zoom into the side where the point Q is and ignore the other tributaries. But we have to take into account if the water goes in those tributaries too, we have to take into account how the water spills. That's the thing we have to sort of keep into account. Now, in the worst case, this algorithm for the point flood will not be any faster than what for the entire terrain, but for most queries, this simple heuristic works pretty well. But if you want to guarantee that all the queries can be answered quickly, then one can do some more pre-processing, which I will not describe here. And that way, doesn't matter what the query point is. If you want to know for a given rain distribution is part of the query. It's not part of pre-processing. For a given rain distribution, you can answer in log n time whether the point will get flooded under the single flow direction model. It is more complicated under multi-flow direction model, and the running time that we have right now is proportional to the number of tributaries. I think it is an open question. I don't know how to do it, is whether one can achieve the same log n query time under the single flow direction model. Now, if you have a reasonable terrain, and if you have hydrologically conditioned the terrain, K is roughly log n, more or less. Okay, let me move on. Now, let me say a few words about the terrain flow query. So in terrain flow query, we have rain distribution that is may or may not change over time. Let's say it is changing over time. What I want to compute is the flow over time. What's the flow rate? Now, why is the flow rate changing? Now, I'm assuming that the water along an edge flows with infinite velocity. I'm not taking into account that the water is sort of taking a finite time to cross an edge. The flow rate changes is because some water is coming directly, but as the other depressions get full, then the more and more water starts coming on some other depressions. So that's the main thing that I'm taking into account, besides the change in the rain itself. Because as the other depressions get full, so it's like naturally like more sort of streams, or they get full, then the more water starts spilling over, and then the more and more flooding happens. So this is what I want to capture. So that's in the model that I have, the flow rate changes because the rain distribution is changing, or some maximal depression fills and the water spills over through a saddle there, and that I call a spill event. So how do I compute this flow rate? What I'll do is I will do two sweeps. First, what I'm going to do, I'm going to keep track of predict. So what I'll do is based on the current rain distribution, I will predict when the different spill events will happen. And I start processing them in the time order. As I process spill events, the flow rate changes, and then when the different depressions will get full, that time also will change. So I update my spill events and I process this one. And when I reach a spill event, I figure out which portion of the terrain the flow rate will change, and I do another sweep like for the flood query downward to update the flows. Okay. So here's what I'm saying, that I sweep across time. So ignore this. I'm not sure why it should start showing the subtitles. So this is what I was sort of saying. When you sweep, when depression gets filled, so some water is coming directly before, but when this is spill events, the more water starts coming here. Then in this depression, for many vertices, the flow rate changes. Okay, so let me sort of tell you how uh, uh, how we handle a spill event. Let me see if I can fix this. But okay. So suppose we reached a spill event, let's say in this this depression beta that got full, and now water starts spilling over. So what I have to do is, I don't care about this depression anymore because this is full. Now, as the water is spilling over from this saddle to this depression, now I have to go down here and update the flow rates of the vertices there. So I start sweeping downward, starting from the vertex A. So from vertex A, I say how much water is spilling from here, and then how much will go along this edge, and how much will go along this edge. So say I figure out how much is going this edge, then I update the flow rate here. And then once you've reached here, then also the water starts flowing from here to G and also to flow F. So I update those also. Then also some water flows along the D, and that water will also reach G. So then again, if I update that flow. So this is for C, and then again, it may change. So this is how I sweep downward and I update all the flows that change. Okay, and I will not sort of go in the detail, but all this can be done quickly. And the total running time that takes is proportional to the total complexity of the flow. Now, sometimes what happens, the water is trickling down and the flow rate does not change much. One can approximate it and one can modify the algorithm so that you don't sort of change the flow rate every time there's a little change. You can change it only when there's a major significant change. So, and one can speed up the algorithm. But that sort of is a detail that I'll ignore for now. Okay, so I'm almost out of time. So let me just conclude by saying that so far I'm assuming that the water is flowing along the edges. So what I do is I look at the edges where there's a lot of water flowing, and that becomes a water accumulation. Those will become kind of a river where the most of the water is flowing across. But in reality, water flows along the 2D channels. So the question is, can I also compute 2D channels? And we have some basic results there. What we do is we are using Manning's equation to compute the 2D geometry locally. And I will not go through this in detail, but I think many of you are familiar. And what I want to say is that typically the Manning's equation is being used, you know, the local geometry, you want to compute the flow rate. What we want to do inversely. We know the flow rate and we want to figure out how high the water there is and what is the 2D channel it is forming. So let me skip this. So let me show this sort of just example here is toy example that originally the algorithm computes this original curve, which I kind of smoothened it a little bit, and then use a Manning's equation to compute the 2D channel. So on this one, you sort of see this original path, and that gives me a profile what the 2D channel looks like. Okay, so let me just conclude by mentioning some of the open problems that we are working or what we'd like to work on. Is so far, what I talked about, all the models were deterministic. I did not include any uncertainty, but there's a lot of data uncertainty because data is either not complete or the data is noisy. Then there's also process uncertainty. So we have some results on modeling data uncertainty, that how you model if I don't have the data complete, or we have some, let's say, pipes, we are not quite sure how we incorporate that. But we have not incorporated process uncertainty, and that's something that we like to do. The second, where we want to extend is the hydrological models that we are using are very simple, and they do some work, and they're serving the purpose. But as we move on, we would like to make them take more realistic models. For example, water flows at finite speed, and have a better model for the 2D water channels and so on. The third thing is, right now all the algorithms are based completely on geometric data. We are not taking the historical data into account. So one of the very interesting questions for me is, how do I incorporate geometry with the historical data? So learn from the historical data and modify the model and do that. with that, let me sort of conclude. Other thing I should say is, because this work has been going for a long time, so we also, because many people were using the software that we developed, so we ended up starting a company, which is now about, I think, 10 years ago, with Lars, who was my long-term collaborator, and some other people. Its goal is to do geometric and topological analysis for terrain models and focusing mostly on the hydrology. So for me, what is sort of really great about is it's a nice cycle, because this company is a good, for me, source of the practical problems that I sort of like to think about, and then some number of the algorithms that we develop get finally implemented as part of the company, and then are being used by many users. So here is some of the users. So these are the 4 papers which sort of contain most of the stuff that I talked about. And finally, these are my collaborators. Aaron Lowe, who is my PhD student. So this is what I talked about, is really his PhD thesis. And Lars is my long-term collaborator. And Matthias and Swain are his PhD students, were his PhD students. So with that, thank you. And I'm happy to take more questions.
Thank you, Pankaj. We are now open for questions. Okay,
so I'll stop sharing my screen.
Yeah, you can stop sharing your screen. And there is one question. Can land cover be incorporated into this type of analysis?
Sorry, Raju, can you say, let me, I'm not sort of able to, can you kick me out? Can you help me? Sure. Because somehow my cursor is not working. Frozen.
I don't know if I can kick you out of.
Okay, so let's see.
Let me see if I say.
Yeah, thank you.
Yeah.
Okay. All right. So sorry, can you repeat the question, please?
Yeah, sure. Elisa, she is asking about, can land cover be incorporated into this type of analysis?
So yes and no. So so here is the sort of the reason that I'm giving ambiguous region. As I sort of said, that in the company part, yes, we have done that, but we had to do much more to add this. To add the land cover in the way I sort of described mathematically, I've not done that from the research front. So I've not, but yes, so there are various things one has to, as long as if the land cover, you can still model as a terrain, then whatever sort of mathematics, what I model as said goes through. But when the problem is when the things are not really a terrain, then one has to do some more stuff. And that one requires some more. So what we have done some of the stuff in the company, but not done in my research. So okay. In principle, the answer is yes, one can do it.
Pankaj, your collaborator Helena is
Hi,
here.
Helena.
Hi, I finally was able to join. It's fantastic to hear.
So good to see you after so many years.
Yes, that's really, really great. Yeah. Oh, this is very interesting work. And what I wanted to ask about is that there are now quite a few models that solve the partial differential equations, shallow water flow, that are used, where you have the Manning's equation, you have the land cover, you have infiltration, and all of these complicated things. So I was wondering, where does this work, like what kind of application do you envision for this work as compared to the full hydrologic models that actually incorporate the entire like flow dynamics? I'm sure that there are applications to that, but
yes. So no, that's a very good question, Helena. So so let me sort of where we have been successful, and there I'll say we have been successful is I'll say in terms of the company, because if the people are willing to pay money to use it.
Yeah, that's absolutely right. Yeah, that's why I'm asking that question. Like, what are the people? What are people using it for?
Precisely. So this model, the simple model I tell you, they don't do a very good job of describing how the water is flowing actually on the surface. But they do a very good job, a reasonably very good job, a good job to where the water gets accumulated. So for example, insurance agencies, they don't care about how the water is actually flowing. What they care about is, will that house get flooded? What's the probability that this house will get flooded? So one of our many of our clients are insurance companies or reinsurance companies who use this stuff. So we have compared with the real data sets where we're just answering the flooding query, which areas will get flooded. They are sort of there, we do a good job. But when you say how the water is really flowing along the surface, hydrological models, partial differential equations will do a much better job. But they're not as scalable as what we can do. So this is a cost that we are paying sort of. And so what I would like to do, which is sort of my second item, was how do I take the, so what I would like to do, and I don't know how to do it yet, and maybe you have some ideas or some of your ideas, is how do I incorporate the two models where you really don't use PDEs in full generality everywhere. You use it when you need them, when you can get away with the sort of this rough estimate what I'm doing, use that. I don't have a good answer to that, and that's something I'd like to sort of think about, that how I incorporate those two things.
And there is a continuum of the
Absolutely.
models, from very simple geometry, essentially what we were doing and what you find in GIS,
yes,
all the way through these more sophisticated models that incorporate some physics to the
absolutely.
dynamics.
So that I think that would be sort of, is really great. So what I need is actually, I need a collaborator. I'm not an expert in that part. I need a collaborator who understands that part, who has sort of good insight what one can do. So I would love, if any of you are sort of interested, I'm happy to talk with you to sort of see what one can do. But that certainly is very interesting. Another question is the learning question. Is, can I, because if I have the flood data because we do have flood data from the past, can I use that to inform the geometric models? So the papers that I have seen, I'm not an expert on learning, but what the papers I have seen in this context, they're just relying on learning, that look at the flood data, pass through the neural net or pass through the learning model and predict. So they're not combining geometry and the learning. And that's what I would be very interested in, combining geometry and learning.
Yes, I would like to point two directions. One is on the learning side, and the other one is, maybe my technical terms could be slightly off.
Sure.
These are like multi-resolution approaches. If you look at climate model, for example,
yes,
right, you are doing at coarse resolution first.
Yeah.
And then if you identify a particular region or cell,
yes,
that there is a potential for, let us say, cyclone, typhoon, or flooding or whatever, the local model is different. Whether form of equations or the model, they are different. And typically those models kick in based on some rules. When you identify certain conditions, there is a separate set of equations, governing equations comes into play, and that is spawned as a separate process to do, because you are looking at higher resolution now.
Absolutely,
locally. And this is, people are doing on high performance computing side.
Yeah, that's right. Yes.
How to distribute this computing. And that is one approach. On the learning side, the inverse, what you are talking about, how to inform these physics-based models, because a lot of these, right? I mean, the things you described are sort of physics-based, right? Physical constraints. Yes. You are modeling the physical constraints, but machine learning models, in general, they are not physics-guided models.
No,
they are
absolutely
data-driven models. And now there is a separate research where people are trying to incorporate physics into machine learning models as a constraint. For example, like your loss equation or something is governed now by the PDEs. That is one approach. Other approach is take PDE where some constants people are assuming, because lack of knowledge or whatever.
Sure. Yeah.
They are assumed to be constants, but now machine learning guys are trying to open that up and try to learn that constant instead of
that's
constant. data-driven approach to estimate those constants.
Yeah. So Raju, what you said is really sort of right. So what my sort of view is like what second thing you said. So what the model I have is like, if I look at high level from a vertex, the water is flowing downward, right? And I sort of say like it goes along these edges. So what I would like to do is, okay, so there's a one graph. Then I use the learning and I add some more edges that suppose I can add some more edges and assign some weight, the water flows along those edges as well. And that sort of makes it more realistic. And we learn the weights of those edges, how much the water should go, basically. So this is what I would like to do. So I have done some of it in the very different setting, is for the taxi driving. Like, so suppose I want to do navigation.
Right.
So then you can compute the shortest path for whatever lost. But then you also have a data that taxi drivers, they know what the best way to go. And they sort of know how to go, and then sort of incorporate the taxi data to learn the weights of the edges so you can compute the shortest path, sort of follow the taxi driver. So I'd like to do something similar here, but so far I haven't done that. But so is there someone else?
Yeah, from the forum, any questions?
No, I'm okay. I need to.
Okay.
Okay.
I have one question,
Sure.
if you guys can hear me.
Yeah, I can hear you, Chris.
Hi, yes. My name is Chris Coffey. It's a pleasure to join. I'm a new student at NCSU, but I also have a background from Appalachian State University in hydrography, particularly in flood modeling up here, especially after our events in 2004, if you remember.
Yes.
And later on, I saw early on, you were discussing the issues of scale and the resolution in your study. And if I may have missed it, I may have walked out, well, yelling child, not so can you repeat just emphasize any issues of scale, any particular findings that you have found relative to scale in your studies?
So what I was sort of saying was that when you don't have high resolution, when you don't have high resolution data, we miss some very fine features, and they may have very big impact on flooding. Like, for example, when a low resolution data, you may miss a dam, you miss the dikes, you miss this, and then all the flow analysis calculations, they're all messed up doing it. And that's why the high resolution data is very important to have high resolution data collect. Now, you don't have to work with the high resolution everywhere. This is what Raju was saying, that like but you need the high resolution data, and then you do processing of doing it. And then so that you sort of one. Now, one thing I completely swept under the rug in today's talk was I cannot work with the raw data. One has to hydrologically condition the data before you start doing any flow thing, doing it. And that's also is very important, how we sort of one does it. But I did not sort of discuss at all in today's talk.
Okay. Yeah. Thank you. I was very curious. We had they just had some intuitively almost results you would have expected when we were modeling the effective scale in an extremely rugged topographic environment up here in Western North Carolina, as opposed to going down to the eastern part with a very, relatively flat environment. And it was strange. We almost got more accurate models on a very flat, poorly parameterized experiment. So I was just very curious. Thank you very much. Thank you. Very good.
Okay, we are about 1 minute from 4:30. The forum typically adjourns at 4:30. However, if you have any questions, we can continue question answer session further, but officially forum closes in a minute.
And also, if you have question to I'm happy to talk later. It doesn't have to be today. And if anyone is interested in talking to them, I'm happy to talk.
Yes,
send me email and I'm happy to talk.
Yeah, one good thing is Professor Agarwal is in our neighborhood, and Helena is already collaborator with him. And anyone interested in, you can reach out to him, and hopefully things will get normalized soon.
And I hope we sort of get to sort of see. So again, let me just sort of thank you everyone for coming to the talk. It was a pleasure to give the talk here, and hope to So to me, one sort of, as I said to Raju in the very beginning, for me, when I go to visit or do, the best part is talking to meeting people. So for me, like, to talk will be successful if I manage to sort of talk with more and can have some collaboration. So I'm very interested in doing it because our backgrounds are very complementary. So we yeah.
Yes. So let us thank, before the forum closes, let us thank our speaker, Dr. Agarwal, for giving one thing I got it from the talk is these are nicely scalable algorithms that we can use in large scale models. Like, for example, I'm thinking on top of my head is we can integrate these kind of flooding models with the large scale models that takes like a day of computing work, like a national water model, for example. Right? But out of the whole days of simulation, only few specific regions are of interest where these kind of models developed by Dr. Agarwal can kick in and do much better job in terms of estimating flood.
That's right. Yeah. So just sort of say complete, because this is how the whole thing had started. Because long ago, there are people in a school of environment. They were doing this water accumulation, and it was taking them more than 2 weeks, and the program was crashing. And they sort of came to me, they sort of asked to sort of say, can we help them? That's how the whole thing started. This was about almost 20 years ago. That's how the whole thing started for me. So thank you.
Yeah,
thank you, Pankaj, and thank you, Raju, for hosting.
Thank you. Bye-bye.
Yep. And there is a post-forum, a graduate, geospatial graduate student post-forum social starting right now. I put the link in the chat.
All right. Thank you. Bye. Thank you, Raju and John.
Yeah, thank you.
Bye.
Bye-bye.
Bye, everyone.